Listen, exploring space inspires the dreams of many, but reaching other planets involves overcoming immense challenges. These challenges stem from the complex blend of science, technology, human resilience, and economic factors. Space travel is daunting, primarily due to the staggering distances between planets in our solar system. For example, the distance between Earth and Mars can reach approximately 140 million miles. Such vast separations mean that even our fastest spacecraft take months to traverse the space between planets. The Voyager 1 spacecraft, which launched in 1977, provides a vivid illustration of these immense distances. It took over 35 years to exit our solar system. This context highlights the need for thinking in terms of years of travel and the substantial energy required to propel spacecraft over these vast expanses. Overcoming these distances necessitates advanced propulsion systems that can efficiently cover large distances. While our current technology relies heavily on chemical propulsion, its limitations are evident for long-duration missions. Consequently, scientists are actively researching alternative propulsion methods that could revolutionize space travel. Options such as ion propulsion, which uses electrically charged particles for thrust, and solar sails, which harness the momentum of photons from the sun, promise more efficient interplanetary travel. These innovative methods aim to reduce travel time and increase the range of human and robotic explorers in space. Additionally, navigating these immense distances involves intricate planning and precise calculations. Spacecraft must follow carefully plotted trajectories, taking advantage of gravitational assists from other celestial bodies to conserve fuel and gain speed. This method, known as gravity assist or slingshot maneuver, involves using the gravity of a planet or moon to alter the path and velocity of the spacecraft. This technique is critical for missions to outer planets, making it possible to reach destinations that would otherwise be beyond our current technological capabilities. In sum, the vast distances between planets present a formidable challenge in space travel, requiring sophisticated propulsion technology, precise navigation, and innovative engineering solutions to bridge the gap between celestial bodies. Space presents an environment that is both hostile and fascinating, posing severe challenges for astronauts and spacecraft. One of the primary obstacles is the vacuum of space, which lacks air and atmospheric pressure. This absence complicates heat management because there is no medium to conduct heat away from the spacecraft, leading to extreme temperature variations. Depending on exposure to the sun, temperatures can swing from minus 250 degrees Fahrenheit in shadowed regions to 250 degrees Fahrenheit in sunlit areas, necessitating advanced thermal control systems. Radiation exposure is another significant hazard. Outside Earth's protective atmosphere and magnetic field, astronauts are subject to higher levels of cosmic rays and solar radiation. These can increase cancer risk and cause damage to the nervous system. Consequently, spacecraft must be equipped with effective radiation shielding to protect the crew, a factor that adds weight and complexity to spacecraft design. Microgravity conditions exacerbate the difficulties of space travel. Prolonged exposure to low gravity affects the human body in numerous ways, including muscle atrophy and bone density loss. Astronauts also experience fluid shifts that can lead to altered vision and increased intracranial pressure. Addressing these issues requires rigorous pre-mission training and ongoing research into countermeasures like specialized exercise regimens and potential pharmacological treatments. The challenge of maintaining life support systems further complicates missions. These systems must ensure a continuous supply of breathable air, potable water, and food. They also need to effectively manage waste products. Developing reliable closed-loop life support systems is an ongoing engineering endeavor. requiring meticulous planning and redundancy to safeguard astronaut health and mission success. Designing spacecraft that can endure the rigors of space travel while carrying essential technology and supplies demands cutting-edge materials and engineering solutions. For instance, spacecraft must be equipped with life support systems capable of recycling air and water and providing food supplies for extended missions. Current spacecraft are often tailored for specific missions, which limits their adaptability for future explorations, making reusability and versatility crucial. Recent advancements like SpaceX's reusable Falcon 9 rocket highlight how innovative engineering can mitigate some financial and material costs. Yet there remains a pressing need for breakthroughs that can extend these principles to long-duration missions to other planets. Developing more advanced propulsion systems, such as ion thrusters and nuclear thermal propulsion, is critical to reducing travel time and expanding our reach within the solar system. Additionally, ground control systems and navigation technologies need to be exceptionally sophisticated to ensure mission success. Autonomous operation capabilities are becoming increasingly important as missions extend farther from Earth, where real-time communication with mission control is impractical due to signal delays. Artificial intelligence and robotics are integral in this regard, performing tasks in hazardous environments and ensuring the safety and efficiency of missions. Another major hurdle is the development of effective radiation shielding to protect both equipment and crew from harmful cosmic rays and solar radiation. Innovations in materials science are essential to creating lighter, more efficient shielding that doesn't compromise spacecraft performance. In-space manufacturing and repair technologies also represent a frontier with immense potential. The ability to produce and repair components directly in space could drastically reduce the need for carrying extensive spare parts and allow for more flexible mission planning. This could involve 3D printing technologies and advanced robotic systems capable of performing complex assembly and maintenance tasks in the vacuum of space. Living and working in space presents a host of psychological and physical challenges that can impact astronaut health and mission success. The confined quarters of spacecraft, coupled with the prolonged isolation from Earth, can contribute to mental health issues such as anxiety, depression, and feelings of loneliness. To address these concerns, space agencies implement rigorous psychological screening and training programs. Crew members learn techniques for stress management, conflict resolution, and effective communication to maintain team cohesion and morale during long missions. The microgravity environment of space also imposes significant physical stresses on the human body. Without the natural pull of gravity, astronauts experience muscle atrophy and bone density loss, making them more susceptible to fractures and other injuries. Cardiovascular deconditioning can occur as the heart and blood vessels adapt to the lower demand for pumping blood. To mitigate these effects, astronauts engage in daily exercise routines using specialized equipment designed to simulate weight-bearing activities. Fluid shifts in the body are another consequence of microgravity, often leading to facial puffiness and vision changes due to increased intracranial pressure. Ongoing medical research aims to better understand these physiological changes and develop countermeasures, including pharmacological treatments and advanced exercise protocols. Ensuring that astronauts remain psychologically and physically healthy throughout their missions is a critical aspect of mission planning. Strategies such as virtual reality experiences, digital communication with loved ones, and team-building activities are employed to keep spirits high. As missions extend further into space and last longer, continuous advancements in both psychological support and physical health management will be essential to overcoming these inherent challenges. Space travel demands extensive financial investment, often reaching astronomical sums due to the complexity and scale of the missions involved. The expenses cover a wide range of needs, including the development and testing of cutting-edge technologies, manufacturing spacecraft and equipment, and conducting lengthy research phases. Launch costs alone can run into hundreds of millions of dollars, as building and maintaining the infrastructure for rockets, launch pads, and tracking systems is both resource-intensive and costly. The financial burden doesn't end with the launch. Missions require ongoing funding for mission control operations, data analysis, and potential mid-mission adjustments. For long-duration missions, such as those aimed at Mars or beyond, the cost of sustaining life support systems and ensuring spacecraft reliability over several years significantly increases the budget. Economic factors also play a role. The volatility of government funding can impact space programs, as budget reallocations or policy shifts may either accelerate or delay missions. Private sector involvement has introduced new dynamics into the space economy, with companies like SpaceX and Blue Origin driving down some costs through innovations in reusable rocket technology. However, the substantial upfront investment remains a formidable barrier. Insurance for space missions also adds to the overall cost. Given the high-risk nature of space travel, securing insurance for the spacecraft, payloads, and crew can be a significant expense, adding another layer of financial consideration. Moreover, international partnerships, while beneficial in sharing costs, require careful coordination and sometimes lead to additional expenses due to the need for compatible technologies and shared resources. Thus, the enormous financial costs involved in space travel continue to be a major hurdle that necessitates strategic planning, international collaboration, and innovative financing solutions. Collective achievement. Furthermore, international collaboration extends beyond just the scientific and technological realms. It plays a crucial role in policymaking, ensuring that space remains a domain for peaceful exploration and utilization. Collaborative frameworks help establish norms and regulations that govern space activities, promoting responsible behavior and reducing the likelihood of conflicts. Pooling financial resources also makes ambitious projects more feasible. The high costs associated with space missions can be more easily managed when shared among multiple countries. The shared financial burden enables the pursuit of more advanced and far-reaching missions than would be possible for any single nation. Through collaborative efforts, nations can address common challenges, such as developing new propulsion technologies, enhancing radiation protection, and improving life support systems. By working together, countries can push the boundaries of human knowledge and capability, exploring farther and achieving more than they ever could alone. Advancements in technology and innovative approaches offer promising solutions to the challenges of space travel. For instance, emerging propulsion technologies such as ion thrusters and nuclear thermal propulsion could significantly reduce travel time to distant planets, making long-duration missions more feasible. These systems promise greater efficiency and speed, thereby enhancing the viability of interplanetary exploration. Robotic systems and artificial intelligence (AI) are also set to play a crucial role. Autonomous robots can perform tasks in environments too hazardous for humans, ensuring mission success even under challenging conditions. AI can assist in navigation, system diagnostics, and real-time decision-making, enhancing the operational capabilities of spacecraft. In-space manufacturing and repair technologies such as 3D printing represent another leap forward. These capabilities allow for the production and maintenance of equipment directly in space, reducing the need to carry extensive spare parts and enabling more flexible mission planning. Such technologies could prove vital in constructing habitats and other infrastructure on other planets. Public-private partnerships are reshaping the landscape of space exploration, Companies like SpaceX and Blue Origin are driving innovation with their reusable rocket technologies, reducing costs and increasing the frequency of missions. These collaborations between government space agencies and private enterprises harness the strengths of both sectors, accelerating technological progress and expanding the scope of achievable missions. International cooperation will continue to be essential. By pooling resources and expertise, countries can undertake more ambitious projects, share risks, and benefit from collective advancements in technology and knowledge. Ultimately, sustained investment in research and development, combined with innovative collaboration models, will be key to overcoming the obstacles of space travel and unlocking the full potential of human exploration beyond Earth.